The following program is brought to you by Caltech.
All right, hello everyone. I hope you all had a good lunch, and we're now here for our last lecture. Our lecturer is going to be Sam Dolinar, another colleague from Jet Propulsion Laboratory. Sam made, in my opinion, his big splash in 1973 in the quantum world when he devised one of the few known receiver architectures to distinguish between two non-orthogonal states, namely coherent states. And after that, he decided, I guess, he had enough of quantum, so he went to the classical world and became an expert on classical coding and has worked on, in many decades on classical codes and approaching Shannon capacities for very challenging deep space communication links that NASA operates. In the recent years, he's come back to the quantum world, is now dabbling again in this area, and today he's going to talk to us about mostly classical stuff, I think, optical communication, specifically free space optical communication. And so it's a pleasure to invite him to give this lecture to us.
Okay. Thanks, Varus. Yeah, there are probably a number of people at JPL who could probably give this talk better than I could, because like Varus said, for most of the 30 years there, I have not really been directly involved in optical communication. But this is just supposed, and in particular, look at Bruce Moyson and Varus have contributed a lot of the slides. In fact, Bruce has contributed most of the slides to this talk. Okay, this is supposed to be kind of elementary. It's not as much elementary as I thought when I was going to present it, or when I started to prepare it. So it's going to get into a little bit of the engineering nuts and bolts. But it's not going to be comprehensive either, and I'll show you that it's going to be basically showing what optical communication issues we deal with in designing and analyzing optical communication for JPL's applications, which are from deep space. I'm not going to get into it all, near-Earth links or networks, either space-to-space or space-to-Earth or anything terrestrial. A lot of the same principles apply, but I'm just going to, I'll follow this basic outline, and as I say, some of the principles carry over to other applications, some don't. We could spend a week talking about optical communication in general. So basically I'm going to give an overview of what a system looks like and what are the capacity limits that govern how fast you can communicate, how efficiently, and how you might use coding to approach those capacity limits, and then all sorts of impairments on the ideal channel. Some that are modeled by Poisson, other models that are non-Poisson models of impairments at the detector, and a biggie, which is atmospheric impairments. Okay, so I'll go one by one and kind of give you in each section a roadmap of what I'm talking about, and just a few slides on each of these. So basically, an overall, why are we doing optical? What's the advantage? So I'll show a comparison of link budget for an optical versus an RF system, and show what an optical system looks like in terms of its components, and then a somewhat more detailed link budget that kind of keeps track of what the losses are, and an example from deep space. So a lot of equations here, and this is going to be true for a lot of my slides. A lot of the equations, but probably there's only 1/4 of the slide area you have to pay attention to. Basically, someone, I don't even know who worked this out, it might have been Bruce or Shervin or somebody, for a particular example of an optical link, comparing a near-infrared optical to a Ka band link, putting in some link parameters that were achievable under certain assumptions, and then comparing the capacity of the optical link to the capacity of the RF link. And basically, the real winning point in an optical link is that you can make the beam so narrow, you get a huge advantage in less beam divergence. And when you add up, taking into account you're using smaller actual apertures, have smaller efficiencies, and basically the net is still a gain. But you can lose the gain with background noise, pointing losses, and other things that are very hard to do optically. So a lot of the engineering that's done in an optical system is to try to keep as much of the theoretical gain. This isn't a maximum, this is a point design, but keep as much of the theoretical gain that you can get. Whoops. Okay, typical optical system. Basically, if we're going to communicate reliably, we're going to need an error correction code and a decoder. Whatever we've coded, we need to modulate it and demodulate it, transmit it over a channel, whether that's deep space with a little bit of atmosphere coming near Earth, to a detector and some systems for synchronizing to what you did and possibly even pulling up other information like ranging information, and eventually making estimates of the data you put in. All these elements of the system are important and need to have analytical models and theories for how well they will perform relative to various imperfections. So a typical link budget will itemize how much power are you going to get and how much are you going to require. And each of these, there's certain loss factors and efficiency factors. That the transmitted power times the gain of the transmit and receive apertures. You lose a lot coming from deep space. This LS is a huge component. You lose more coming through the atmosphere. There's some efficiency with your pointing, some transmit and receive efficiencies. These are basically all just multiplicative factors that keep track of the power that gets to you at the receiver. The required power under ideal conditions would be something called P sub I. Now that's going to be, it's going to require a lot of math and models to determine what that is given the received. But whatever you calculate, there are other losses that govern that. And so these tend to be things, some of them are multiplicative losses, just like these are, but they're kind of on the receiving end. So we have to account for those, and this talk will cover a good number of those, not some of the obvious ones like space loss and antenna gains. To give you some feel for what happens over the course of a mission, I've drawn kind of a rudimentary diagram of what happens when Earth is trying to communicate to Mars. At different point in the orbital period, Earth will be either really close to Mars or really far from Mars, and that differs by about a factor of 4. So the signal power, no matter what you're sending, is going to change by about 12 dB over an orbital period of 2.2 years and some months, I think. And furthermore, when you're on the opposite side of the sun, you're looking through the sun, so the noise coming from this link is really bad in the worst case. So basically, you're going to have a typical pattern. These are different dates, but a typical pattern of signal that varies with time, noise that varies with time. Your achievable data rate will vary with time. You have to design a system to do that. And these are some of the system parameters that I'll talk about later. They also should be adjusted with time. OK, so back in that block diagram, one of the things that was very important was how do we detect the signal? And here's already a big branch. Do you do it coherently or non-coherently? I'm going to talk in this talk mostly about non-coherent detection because that's the best for energy efficiency, which we're most concerned with from space. For non-coherent detection, intensity modulations are fine. And that produces a photon counting channel model. And then given a channel model, how do we process the observed photon counts to recover the data? That's what I'm going to talk about in this section. Detection methods, as I say, basically divide into coherent and non-coherent. Coherent, and I'll say a little bit about it on the next slide, but then I'll be done because the rest of the talk won't be dealing with it. Non-coherent is like very simple because it just requires a photon counting receiver, and it also, this is a hint of something that I'll show later on that shows the capacity in terms of power efficiency is unlimited for non-coherent with low duty cycle on-off modulation. So as I said, this is going to be my only slide on coherent detection systems. Heterodyne and homodyne are really state-of-the-art system, and they have really a lot of advantages that they can use them with arbitrary coherent state modulations. And they achieve much higher spectral efficiency than the non-coherent system. So if your application requires a very high data rate, and even with a lot of bandwidth to burn, these tend to be the right system to use. On the other hand, when we're starved for power on a deep space link, we look at the opposite and say, well, we don't care so much about the spectrum. Number one, we don't even have enough power to support a really high data rate. Maybe we're at megabits per second instead of gigabits or terabits per second. And second, we really, really care about the energy efficiency. So coherent systems have all kinds of widespread applications that I won't touch on, but as I said, that's a topic for another course. The one thing that kind of limits them with respect to photon efficiency is that as soon as you use a coherent receiver, you have brick wall limits on the maximum achievable photon efficiency, either 1 nat per photon or 2 nats per photon, and that is a natural logarithmic unit corresponding to 1.44 bits. So you can get about a bit per photon or 2 or 3, not even 3 bits per photon, but you can never do any more than that. Right now, I'm involved in a project where DARPA is pushing us to try to get 10 bits per photon, and such solutions are just out of the question. If you want to use non-coherent detection, basically, how do you design the signal? Basically, you just need to have some kind of waveform that communicates your information. And the real simplification is that waveform doesn't have to be too complicated. That if you just have kind of a slotted type of waveform where you put a certain amount of energy in a slot or no energy in another slot, except with noise, you're going to probably detect something there anyway. But that is pretty close to being optimal. So just binary and slotted does the job pretty well. So what's the actual modulation scheme we would use? Simplest thing, like I say, is just turn the laser on or turn the laser off in a pulse and put a bit of information that says whether it's on or off. Now, for energy efficiency, you can't make these equally likely. If you make those equally likely, you're back to the same brick wall limits again. You have to, for the way you get the energy efficiency is to hardly ever use the on pulse. So the probability of the on pulse is very small relative to the probability of the off pulse, because the off pulse doesn't cost you anything. So when you have a low duty cycle, then pulse position modulation is kind of a more regular form of this. It says instead of flipping a coin with a very small probability and producing a 1, how about putting exactly 1 out of every m slots? It's more or less the same thing as saying picking a 1 with probability 1 out of m. So this is an illustration for m equals 16, occupying slots 0 through 15. The modulation rule says put 1 pulse in there and only 1. Where can you put it? You can put it in one of 16 slots, which means you can encode log m, or in this case log 16, 4 bits of information. You could basically take a 4-bit sequence and put it into the slot that corresponds to its numerical value. A 4-bit binary sequence. So 0, 0, 1, 1 would be like 3, and that would be this pulse right here. As I say, ppm is pretty near optimal. I'm going to be using ppm and OOK pretty interchangeably throughout this because I'll be dealing in the region where OOK and ppm are pretty close to the same performance. Once you've done that, once you've done ppm or on-off keying modulation, so either on-off keying with probability 1 over m or ppm, which is 1 out of m slots occupied by a pulse. And you transmit it, and all sorts of funny things happen to it along the way. And finally, you detect it with a photon counting detector, which could introduce there could be some noise coming in from the channel. There are dark noise events introduced at the detector. Synchronize it properly, and you notice you count some photons. The channel model for this is a Poisson channel model. What you get out of here is dependent on how much power you put into it, and that's the mean of a Poisson process that tells you the probability. So even if you put power in here, you're not necessarily going to see a photon, because with probability 0, a Poisson probability with a certain energy still has a certain probability of 0. And conversely, you could have 1, 2, 3, 4, 5. Once you've done all this, how do you put all this together to communicate the data? Here's kind of a very simple schematic of, suppose we had a data sequence. I say we're going to code it. I'll get into that a little more detail later, but first step is to code it. So compute some parities. The 1 could be computed as a parity on some combination of these. Maybe it's 1, 2, 3, 4. Like if it's the first 4 bits, the parity of that is a 1. If that's the rule for that parity, then that's a 1. Anyway, have some number of parities. You have to compute a rule for computing parities. You transmit both the information and the parities. And what you're going to detect now are spikes that correspond to photon counts. Photon counts, once you've synchronized everything up, you put them into their slots, and maybe you see two counts, no counts, 1 count, 2 counts, et cetera, in each slot, and you figure out where you saw pulses. Well, in this case, you would make an estimate first of what the coded word is, and then, so you probably estimated originally that there was a 1, 1, 1 here, that there were pulses here, and then look up your decoding algorithm to say that would recover that information. Okay. This is one, when you're processing the data, there's a subtlety. I showed you basically just counting up whether you saw a pulse or not, counting up, kind of just making an ad hoc decision. I converted this to a 1 or a 0 based on sometimes I saw 1, sometimes I saw 2, sometimes I saw none. In general, you should do soft decisions, which is depending on how many counts you see, how many Poisson events you see in a slot. You should compute probabilities associated with that event versus what you thought you sent, versus all the possible code words you could have sent. And the decoder should then take advantage of the computed probabilities rather than for you to say, well, I'm going to convert this to pulse and this to not pulse right away. So, and then there are all kinds of ways that you can vary. Bruce just gave me this update here. It's a hard decision. Well, does it mean you always make a decision? Or sometimes if you're trying to decide on a ppm symbol, which is, you know from the modulation rule, there can only be 1, but suppose you see 2 slots with 2 counts, and that's the most. What do you do in that case? Should you flip a coin, or should you just say it's a tie and I'm going to call it an erasure? The same thing that you would get if you saw no counts anywhere. So basically, you do a little bit better if you erase the ties, but you do best of all if you do soft decisions. And just to show a real high-level chart on how, in the typical Earth-Mars link, if the noise and the power in the signal photons are varying over the life of a mission, then sometimes the optimum first of all, the data rate will change over the life of the mission. I already showed you that. And the optimum ppm order that you choose will also vary over the lifetime of the mission. So this just gives you some representation of if your channel conditions are not constant, you have to be able to cope with a wide variety of changes in the system parameters, or else it's not going to be anywhere near optimum. So basically, that's the idea there. Okay, how am I done? Now, I want to put all this into perspective. How well are we doing relative to how well we could possibly be doing? Okay, here I'm going to put up something that Vittorio even pointed out. Basically, the Halevo capacity represents the ultimate limit of what any system that's any quantum consistent measurement could do. And what is that, basically? What's the Halevo capacity? These ad hoc systems that I've put up, PPM with photon counting or coherent detection or anything else, how do they relate to what you could ultimately do? Okay, and this is very nice and not easy, but it's now well known after a number of people have calculated what the capacity is for a pure loss system, which is really only affected by the inherent uncertainty in quantum measurements. What I call it quantum noise. So throw away all the background noise, throw away anything that has to do with the atmosphere. What's the limit to pushing the limit of a quantum measurement? We reformulate the capacity measurements in terms of a capacity trade-off. I already alluded to this in the coherent detection slide. Namely, if you want photon efficiency, if you want to be very energy efficient, you give up something in terms of spectral efficiency. More generally, we're going to call that a dimensional efficiency. Usage of bandwidth is one element of the possible dimensions you could use. You could also use spatial modes, but mostly I'm going to say we have one spatial mode, so dimensional efficiency is the same as spectral efficiency. So photon efficiency, which I'll call PIE, is measured in bits per photon. Dimensional efficiency is bits per dimension or bits per second per hertz per spatial mode, and I'm going to assume one spatial mode. So basically, it's how efficiently are you using your bandwidth. I'll show you what PPM plus photon counting does, and is there any way to get better? Is there any way to do it better? And finally, I'll deviate from the pure quantum noise model and say, how about channel capacity based on a Poisson model that takes into account noisy PPM? Okay. I apologize for a little notation. When I write papers, I can't write DIE and PIE in equations, so dimensional efficiency is abbreviated C sub D, little c sub d, and photon efficiency is little c sub p. So any place I've taken an equation out of LaTeX, remember that's dimensional efficiency, which is the same as spectral efficiency for all purposes of this talk, and CP is the same as bits per photon. And this was derived, the equation from this was derived from a paper by Vittorio and Jeff and other people, right? But put in terms of DIE versus PIE and taken to the limit of large CP, large photon efficiency. It's basically an exponential decline of dimensional efficiency with photon efficiency, except for this linear multiplying factor here. So it falls off exponentially except for the multiplicative factor. Why is that important? Well, if you look at equations analytically for PPM with photon counting, you find out that the optimum M that you should be picking is roughly 2 to the photon efficiency that you want to achieve. And for that, the corresponding dimensional efficiency also goes exponentially decreasing with photon efficiency, but by a constant factor. It's missing that linear term. So that's the difference between absolute optimum Halevo capacity and this ad hoc system that I'm going to be spending most of the time talking about. If you take the ratio of those two things is about 2.5 times the photon efficiency you want. So this is not insignificant, where DARPA wants us to reach a photon efficiency of 10 bits per photon. 2.5 times that is about a factor of 25. So you can do a factor of 25 better if you could find the optimum measurement that's consistent with quantum theory rather than the ad hoc measurements of ppm and photon counting. Modulation and measurement, not just measurement. So, okay. Yeah, and I say, can we do better than this is the question. Well, one of the things that Barris introduced me, going back 40 years, I had this receiver that was the optimal hard decision measurement on an arbitrary binary coherent state alphabet. In other words, if you want to decide, did you send this coherent state or that coherent state with minimum probability error, this receiver structure, which is illustrated here, gave you the minimum probability error consistent with quantum measurements. We've also shown that it's a soft decision measurement for maximizing mutual information, at least with respect to BPSK modulation. But unfortunately for BPSK, it encounters exactly the same limit as homodyning, and for OOK, the difference between it and direct detection is so tiny it doesn't even show up on the graph that I'll show you pretty soon. We thought we'd had a bright idea to maybe inherently there was something about the donor receiver works with a feedback that works to interfere with the incoming field before it's detected, and then it's photon counted. So it has a structure which is ideally implementable, and some people in the last 5 or so years have actually done this in the lab. But we thought, what if we had coded symbols rather than one, and kind of had a loop with something with one of our decoders, like we use for iterative decoding of LDPC codes or turbo codes, fed all this back, but the answer is nothing. We didn't get any improvement. So here's kind of the summary of where things stood at least a couple years ago. The ultimate limit, the high-level limit, is way out here. This is dimensional efficiency or spectral efficiency per spatial mode versus photon efficiency. And you can see these curves drop off very, very steeply. These are logarithmic plots in both directions. Nobody knows how to get to this curve except with a known receiver structure, basically. With something like ppm and photon counting, we follow this curve. We can't do any higher dimensional efficiency than 1/2 for ppm of order 2. For OK, we could do a little bit better and actually get up to 1 bit per dimension by basically making it probability 50-50. But when you make the probability 50-50, your photon efficiency goes away. So if we want to explore this region, both ppm and OK approach the same limits, but they're demonstrably different than the high-level limit, especially if you're measuring this vertically. That's that factor of 25 at 10 dB, or 2.5 times the distance you're going on this axis. There are a lot of systems, demonstration systems, JPL, Lincoln Lab, maybe some other places, that were getting in the neighborhood, pushing in the neighborhood of 2 bits per photon, even 3 bits per photon, depending on exactly how you're counting photons. This is basically bits per detected photon, is what I'm assuming here. With the DARPA project, we recently did a lab experiment that was explicitly designed to push in this direction to get 10 bits per photon, but at very minuscule values of spectral efficiency. So that's kind of the lay of the land. And if you see a donor receiver with BPSK, I don't even know if you can see it. It's basically hitting the same brick wall as homodyning, and donor receiver with OOK. With some magnifications, I can tell a difference, but basically it lines up exactly with OOK and photon counting. So can we do any better? Well, yeah. One way to do it is to go into the quantum world and say we're not going to send coherent states. We're going to send ideal quantum states, number states, where we just, at the transmitting end, concoct a quantum state which has a prescribed number of photons. In other words, it is an eigenstate of the photon detection operator. And if you put one photon or two photons or three photons, that's exactly what you're going to get, provided you transport it from the transmitter to the receiver and nothing happens along the way. So basically, this is a nice model. It ends up with, I'll show you on the next slide, with perfect transmissivity, eta, from transmitter to receiver. It gets you to the Halevo limit. It basically gets you there at high photon efficiency. It gets you there even only using 0 and 1 number states. You don't even have to use the 2 number state, 3, 4, 5. You would if you wanted to trace out the whole Halevo curve, but not if you're just interested in high photon efficiency. So, and basically it's a channel model that's very much like the erasure channel model, ideal erasure channel for a PPM or an OOK channel, for, so say, a PPM channel, where a 0 without noise always gives you 0, but a 1 will give you a 1 if the transmissivity allowed it, or sometimes it'll get lost. Calculation on this is asymptotically, if you just use 0 and 1 number states, and you use them in the right proportions, just like you would for OOK, you can achieve a dimensional efficiency which, relative to the photon efficiency, is to the minus photon efficiency, but including this time the linear factor that was there in the Halevo bound, but a multiplicative factor that's a little bit different. So this is exactly the asymptote of the Halevo bound, and this factor is less than 1. It goes to 1 if transmissivity is perfect, but otherwise it's a number less than 1, and that's the price you pay relative to the Halevo bound for using single photon number states. So Barris has plotted a whole bunch of cases for different etas. Halevo bound is way out here. OOK performance is here. And all these other ones are different values of eta. So if eta gets really bad, it's worse than OOK plus photon counting. But the closer you can push the transmissivity to 1, the closer you approach to the bound, and it tails away due to him only using 0 and 1 number states, whereas if he was interested in this part of the curve, he could use more number states. Okay, so number states are hard to produce. What if we wanted to have, for the best of both worlds, use photon counters, which we like, which are nice and simple, but also use coherent states, which are nice and simple to generate? So this was kind of a weird idea that is very impractical. Let me just emphasize that right off the bat. But it's a nice mathematical construct to kind of let you see what may be behind some of that, the efficiency you can get with the Halevo bound. You can try to mimic a single photon number state by using a coherent state, but having feedback from the receiver that tells you stop sending as soon as I have a photon. In an ideal channel with no other noise, 1 photon is enough to say I've got a signal. It's a Z channel, just like that other channel. So why send anymore? Anything after that is wasted. So if you could do this by magic or whatever, the transmitter only spends this much time and doesn't waste the energy from here to here. So there's an economy factor. Now, unlike the case of the number state, there's also a price here because you're increasing the transmitter bandwidth. You're increasing a whole lot of other things too, like the cost of the feedback link and everything. But I'm saying intrinsically, you're causing this pulse to shut off sooner than it would have, so the bandwidth increases. What happens is there's a factor D by which you save photons, namely the average of the stopping time versus the full symbol interval if you were to transmit for the full symbol interval. But 1 over that is also effectively the amount by which you're increasing the bandwidth usage. So the same D factor, you increase bandwidth and reduce photons by the same factor. That's a real good trade when we're pushing for high photon efficiency. It's actually a very bad trade if we were pushing for high bandwidth efficiency. So you just never do this in that region. But it works out to be a good trade here. So pretend that you could do the feedback instantaneously, pretend you could do it without cost, pay only the inherent bandwidth price on the transmitter. What's the capacity efficiency? Well, the dimensional efficiency as a function of photon efficiency is the Holevo asymptotic, again, for high photon efficiency. It's the asymptotic formula for Holevo times a constant factor again. But this time, the constant factor depends on how many photons you put in the pulse that you might have been erasing. So if you had transmitted for the whole symbol period, epsilon is the probability that you would have seen something. That actually turns out to be something you should optimize over. You don't want that to be 1. You want it to be, in this case, 0.88. Was that for OK or ppm? I forget. You get different values whether it's, anyway, and the bandwidth expansion of the photon economy factor is about a factor of 2. You're planning to send a pulse of about 2 photons. But you only send 1 because immediately if you see more than that, you would. So summarizing, that there's this is kind of an impractical, the single photon shutoff is impractical. This could be practical as better sources are being developed, but they share a lot of features in the sense that unlike ppm or OK with photon counting, there's no multiplicative factor, no linear increase in the difference between Holevo capacity and this capacity for higher and higher photon efficiency. It's only multiplicative factors. And the multiplicative factors, the best case is transmissivity 1 for single number states. You could get up to a factor of 1. ppm, you can also do ppm modulated number states, and you never get there even with perfect transmissivity. You only get to 1 over E. With single photon shutoff, because of the bandwidth penalty, these ratios are a little bit less. Okay, Poisson. Okay. Yeah. We throw noise into this. Those other capacity models no longer apply. You can try to derive other capacity models, but let's go back to the real world and say when we put noise in, we use a Poisson model. What's the capacity of a Poisson system? Well, we use it for a lot of detection of signals and background noise, but unfortunately it doesn't have a closed form solution. So, but Bruce has worked out some analytic here where he's divided the, he has an analytic approximation to the capacity formula for the Poisson capacity where it's a ratio where the denominator depends on contributions from 3 types of terms. And these correspond to differences in different regions where different formulas, where different ones of these terms are dominant. So the first one is what he calls a noise-limited region, where the capacity is quadratic in the signal power. Then the quantum-limited region, where it's linear in the signal power. And finally, the bandwidth limit where you just saturate at whatever your bandwidth is. No matter which of those capacity formulas we think we have a system to aim toward, capacity only tells you theoretically how much information you can jam through a system. To do it reliably, you have to do it with a code. And if you have a finite length code, you never get quite to capacity, and you never get quite to zero error probability either. So it's always a trade. How close can you get to capacity? If you look at, if you remember the loss equations, we're enumerating capacity as an efficiency rather than a gain, because we're measuring things with respect to the capacity limit. So typically, if you have a system that has a code on it and it has a certain amount of power, and you have a specific code, this one's plotted backwards from the way I was plotting the other ones. This is photons per bit measured in dB, because we typically, in the RF world, plot EB over N0 as a signal-to-noise ratio, and we're used to seeing waterfall curves like this for error rate versus power used. But there's a capacity limit. Capacity limits could be constrained to the rate of the code you're using, so that's why 2 limits are shown here. But for a given code, the performance doesn't exactly, it should, if the code were ideal capacity achieving, it would be a vertical performance curve at the capacity limit. It's not. It falls off at a slope that's not vertical, and it's a certain distance away, depending on what error rate you want to measure the distance at. So people, well, let me just go on from there. How can we choose a code? Again, this has been a result of several studies over the past decade. Reed-Solomon is a natural choice for PPM because basically a PPM symbol, Reed-Solomon wants a symbol, the alphabet of Reed-Solomon code is a symbol in a higher order alphabet, and it can be matched with the PPM alphabet. So, and a lot of work has been done on that from 3 decades. There have been, since the advent of iteratively decodable codes that use soft decision information. Reed-Solomon information only uses hard decisions or hard decisions including the possibility of an erasure. There's also been some recent work on getting soft decision Reed-Solomon decoding algorithms, but that generally hasn't been very valuable for this problem. The more practical types of soft decision decoding problems are parallel concatenated convolutional codes, serial concatenations of convolutional code with PPM, and LDPC concatenated with PPM. So an example of one such code called serial concatenated convolutional code with PPM uses PPM, basically, PPM itself is a code. You can consider it as a very low-rate code mapping those 0 and 1 on-off symbols into a longer string, which is forced to have only one on signal. Have a convolutional encoder as an outer code, a bit interleaver, and what's called an accumulator. And I'm not going to get into the details here, but basically in the LDPC world, this is used a lot as part of an LDPC code. But in this particular application, Bruce has concatenated it with the PPM modulation, which is what's important for making the low duty cycle overall. This much up to here without the PPM would have a duty cycle of 50% ones and zeros, and that wouldn't be any good for energy efficiency. So Bruce has plotted some performance curves, and that's why he likes this one the best, but it's still some distance from capacity. Okay? And I'll just emphasize that regardless of which code we're talking about, we now have gravitated to, people for 40 years have talked about, oh boy, how much coding gain am I getting with respect to uncoded? And because the capacity limits are what really define the target, the best you could possibly do, the code's job is to get as close as that as it can. So, and with the advent of iteratively decodable codes like LDPC codes and concatenated convolutional codes and turbo codes and stuff like that, you can get pretty close to this. So it actually makes a lot more sense. These are small numbers now, deviation from capacity. And they're like numbers that should be tabulated in a loss equation, a loss in the link budget. So aim for capacity and say how far away from the capacity can your code get. Okay, now I'll briefly say some words on the Poisson modeled noises that gave that Poisson capacity that I talked about just before the coding section. One thing, I think this is still a conjecture, Jeff, the Holevo limits for add pure, but it's a widely believed conjecture. Is that right?
It is certainly an upper bound on capacity.
Okay.
And all the information we have supports it to
Okay, but upper bound is also very useful for what I'm going to put on the next slide. It's sufficient.
It's a lower bound.
Oh, okay, then maybe not.
It's a lower bound, but all the evidence still supports the
Right, right. Okay. Anyway, so the Holevo limit that I plotted on the previous graph for the noiseless case, i.e. only quantum noise, has a very simple form, and it's conjectured if you add thermal noise that it has a similar form. This is a this G function has that very simple form. And basically, you just have a difference of this G function with the amount of the background noise. If you plot this function, you find out that the green one there is the noiseless. Add thermal noise of 0.001 photons per mode. It tracks pretty well up to a point and then falls off as a function of photon efficiency.
0.001 is a very high number compared to looking at the blue sky.
Okay. Yeah, so the less, you fall off less the further out you push this, basically is the message, right? Okay, what Bruce calculated is basically, as I say, you can't really calculate, the Poisson capacity isn't known in closed form, but you can show some things about it. And in particular, that if you just use Poisson capacity for signal plus noise, you would get a photon efficiency that was not bounded, whereas this conjectured formula for Holevo capacity is bounded. So what I believe that means is basically the Poisson approximation is just not exact in this case, and you have to go back to a more exact model called a negative binomial model. But again, it's still widely used for thermal noise in a lot of cases. Where the Poisson model is producing results that don't conflict with the presumed Holevo bound for thermal noise. Here's one of the areas. It can be used for modeling what happens when your laser does not have an infinite extinction ratio. A non-ideal laser will transmit, you can tell it to be on and then off, but some of the power is going to spill over into the slots where you don't want it to be. And how much does? Well, the model is that it's proportional to the amount of power you transmit in the on state. So, and that proportionality constant is called the extinction ratio. So with a finite extinction ratio, you use a Poisson model on signal plus noise, and you find out that the photon efficiency is strictly bounded by something that's like the log of the extinction ratio. Second type of noise that always comes into a problem, a optical communication problem, is dark noise at the photodetector. With different devices, you have different levels of dark noise. And depending on the level of dark noise, the Poisson model computes the point at which the capacity efficiency curve will deviate from the ideal case of no background noise. So a lot of the game, when we want to get to high photon efficiency, we basically, once this deviation occurs, we have to have a device that has a low enough background, low enough dark current that will follow this curve, the ideal curve down as far as we can. Okay. Another interesting analysis result is, even though for dark noise, this curve back here, for any one of these, there is no limit. If I plug in a 10 to the minus 6 background, or 10 to the minus 5, 10 to the minus 4, it will theoretically go on forever without an upper bound. On the other hand, it's effectively bounded because it falls off as 2 to the minus something times the photon efficiency, where that constant is itself something times 2 to the photon efficiency. So even though, we used to think that this was a brick wall limit. It was just empirically, it fell off so fast. But analytically, it's that, but it's effectively just as bad. If you look at where this limit crosses what am I trying to say? It crosses the noiseless curve here at roughly a photon efficiency of something that's proportional to 1 over the amount of background. An actual curve, so that's this vertical dotted line here. An actual curve will deviate away from the ideal OK curve a little sooner than that. And Bruce estimates like another factor E cubed in the logarithm. So log of this value versus log of this value is the difference between that dotted line and that dotted line on this axis. And log of E cubed is about 4 bits. So somewhere in there is the best analytic model we have for how quickly dark current or background noise will start to kill you. And translating, remember the optimum I gave you for the optimum M value of ppm. If you plug in the optimum ppm and multiply it by the NB that fits into this formula, basically you need to have this product, because M is basically proportional to 2 to the CP, remember. So this product has to be no worse than like 1 over e to the 4th, certainly no more than 1 over e, which is the total number of noise counts you can tolerate throughout the whole ppm symbol. So if you had ppm 2 to the 10th, 1,000 slots in a ppm symbol, you need to have a fraction of that noise throughout the whole symbol, or that fraction divided by 1,000 in a slot. Or you start to pay a big price. That's the basic message here. So I told you that extinction ratio by itself results in a brick wall limit. For instance, 44.5 dB extinction ratio is what it takes to get 10 bits per photon. If you add dark noise, if you try to do analysis that involve both, then analysis basically gets more complicated. These curves are for different values of M, and basically you always want to be on the outer envelope of the curve, or where the curve turns back. You want to just kind of stop there. But anyway, that kind of gives you, okay, I'm very quickly running out of time. So I will say there are other losses that we have to consider in the system that are not additive losses. One of them is detector jitter. Detector jitter is a delay from the time a photon is incident to the time a photon electron is detected, and depending on your device technology at the detector, you can have what looks like a very sharply defined time or a wider defined time. And the important value here is what's the standard deviation of the jitter relative to the slot width. Depending on that ratio, jitter, if that ratio were big, jitter doesn't allow you to get anywhere near the ideal curve. If that ratio is small, conversely, you're almost right on top of the curve. So it's kind of a benign effect as long as you can keep jitter in the ratio of the jitter to the slot time on the order of 0.1 or so. Photodetector blocking is another effect that you have to consider in real photodetectors, that there's a dead time after each photodetection event. So you should be seeing an event here, 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 but after blocking, the ones at the dotted line you don't see. How can you model that? Basically, it can be modeled via a Markov chain, because you just basically say, if you've already seen something, you're dead to the world for the next amount of time. This dead time is fixed by the device. And the important parameter is the dead time times the rate at which photons are coming. So if you want to reduce the effects of blocking, you want to reduce the rates at which photons are coming. The straightforward way is to increase the slot width, but that hurts the data rate. You can do it spatially by defocusing the beam. And when you do that, then there's some more analysis you have to do to analyze what happens when you diffuse the beam onto an array of detectors. A Poisson model is a pretty good model for the output of this array of detectors. And you calculate what the effects of blocking are. And basically here I'm just going to kind of show you one kind of summary graph that says when you put all these things together, all of the bad effects, the blocking effects, the dark noise effects, the jitter effects, for different technologies, with single photon nanowire detectors being the best technology in all these areas. You can either start to deviate very significantly from the ideal curve or very small. And you know, we are always aiming to have devices such that we can control all of these effects so that we'll still be on top of the ideal curve. Finally, the last thing I'll talk about is atmospheric effects. Even though from space we can have pure space-to-space links, and a lot of times we've talked about having a relay station around Earth. But the more typical application is we have to get the signal down to Earth. And we have the signal down to Earth, we have to deal with the atmosphere, the last bit of the communication link. So I'll talk about some of the effects of the atmosphere, largely leading to fading channel models and how we mitigate the effects of fading. So here's just kind of, I guess I put the same information on the previous slide. I don't really need to say it because some of these pictures will be repeated. Background, scattered light. Again, you have pictures of what the sky radiance looks like in the daytime and how much, you just have to calculate how much you have to deal with. That fits into the noise power in the background in this capacity expression that you saw before. And so there's nothing new here. It's just this is one of the ways that one of the ways that the background comes from. And the point here is, a very large background, it pays to go over to coherent detection. Atmosphere can also scatter. So you also see diagrams like this where you see the atmospheric absorption, scattering and absorption, basically. The absorption has different absorption bands. You want to make sure you're transmitting at a frequency that's not absorbed, but then you have to still account for it. The more complicated thing is what happens in the case of clear sky turbulence. And for an asymmetric link like we have, it's a little bit different depending on which direction you're going. From space to Earth, as I say, the atmosphere is here at the receiver, and you have a long distance of pure vacuum till you get there. And you have problems with angle of arrival and scintillation causing fades. From Earth to space, basically you have beam wonder and beam spread to worry about because the atmosphere affects the beam early. So with beam wonder and beam spread, I'm not going to say too much about that. Basically, one is an attenuation and one is a scintillation. It's sort of like the scintillation in the other direction that I'll talk about in more detail. For this general scintillation model, you have temporal distortions. Basically, the power varies randomly over time, and there's a coherence length and a coherence time to these variations. It can be modeled with what's called a scintillation index. What's the variability of the amplitude variation in the signal? And it's modeled with a log normal distribution with a certain sigma parameter. And that sigma parameter is called the scintillation index. How long does it stay? How long does a particular amplitude stay in duration? That's the coherence time. It's very highly correlated over short time intervals. And so coherence times can be computed from a inverse bandwidth type of calculation. And typical coherence times are on the order of milliseconds, 10 milliseconds, something like that. So this induces a very simple model for analyzing most scintillation effects, what's called a block fading model, where it's a two-parameter model. You pick a normalized power out of a log normal distribution that has this scintillation index, sigma I squared, and you allow it to last for a coherence time t, for the coherence time. Then you flip another random coin at the end of that coherence time and figure out what the amplitude is for the next. Okay? You get a very similar model from pointing errors. So again, a pointing model introduces fades that last for a certain period of time, and they're, I'm not going to get into the exact statistics on I don't know what the statistics are, the pointing statistics versus the atmospheric statistics. But at the high level, once you have a model for a block fading model, then these are very similar. What does the effect of, say, a block fading model have on performance? Well, it causes outages. Typically, fades last for a long time relative to the length of a code word. So a code word isn't going to be able to average over many fades. Here's a picture, a code word lasting 0.06 milliseconds is the gap between the left and right of these blue lines. You can hardly even see it, and it fits within one fade. So basically, one code word is going to see one level, and next code word is going to see this level and have way too much power to burn. And next code word is going to see that much, and then one's going to see this one, and another one's going to see that. And all these code words are going to fail completely. So you can't possibly have reliable communication if that's all you're going to do. So you either accept that you have a significant performance loss and a very shallow sloped error probability curve, or you have to figure out a better way to combat the fading. And a standard way to do it, which we can use in deep space because our data rates aren't that high, is to use a channel interleaver so that fades that last a long time, an interleaver can break them up and kind of mishmash all the fades together. So a code word will see, a single code word will see a lot of samples from different parts of the total time spectrum. And the result is, with different amounts of interleaving, you can start moving toward capacity. Now, the one thing that you're never going to do is any better than what's called the fading capacity. So if your channel model is different capacities over time, the time averaged value of that capacity is the best you're ever going to do. You're not going to be able to do as well as you could do if you had constant power, the power that you're investing over the whole period of time. The fade reduces that inherent capacity to something called the fading capacity, but with interleaving, you can recover the performance loss and move it toward the fading capacity limit. I think I already had this slide. This is a kind of a duplicate. This is a duplicate of pretty much what. Basically, we're averaging over different channels so that this waveform, a code word now gets samples from different parts of this waveform, that being one code word now on that scale. Yeah, okay. This is a more complete graph showing with different levels of interleaving how you can bring the performance curve close to the fading capacity threshold, but you always be away from the no fading capacity threshold. You can do some analysis of this and get some analytic formulas as to how you expect these two loss components to vary with the fading parameters. Number one, the fading capacity loss, which is non-recoverable. With some approximation, you can say it's linear in the scintillation index, sigma squared. The finite interleaver loss for a given size of interleaver goes as the square root of the scintillation index, just as sigma. And the other thing that's important and that precludes this as a solution for a lot of really high data rate applications is that how much memory do you need for this interleaver? And basically, you calculate how many bits fit into a coherence time, the product of the data rate times the coherence interval, and how many fades do you want to average into each code word so your code word sees a representative sampling. And that's how big your memory size has to be. And with that, you can get, as I say, this approximation as to how much you lose relative to the ideal case if you didn't have the fading. Okay, so end of my talk, and I'm over. Okay. So potentially, there's always been a lot of dBs there for free space optical to gain over RF systems. The idea is to actually get those gains, you have to make a system that controls all these other parameters that are conspiring to make those gains go away. There isn't, and if you're interested, as JPL is, in photon efficiency, there's no theoretical upper limit. If you can make all the other noises go away except the ultimate quantum noise, you could have arbitrarily high photon efficiency. Unfortunately, you have to pay a big price in terms of spectral efficiency, even at the quantum limit. Now, intensity modulation plus photon counting does a pretty fair job of getting there. You can get arbitrarily high, in principle, suboptimal spectral efficiency with respect to the quantum limit. Ideal number states can get there in the limit of perfect transmissivity. To do anything, whether it's ideal or whether it's the other systems I was showing using actual noise and impairments in the channel, you need appropriate error correction codes. And that's another, it's still not solved area. You know, basically, every time you, there are different codes that are appropriate for different purposes, and I haven't even touched on how to, that whole section could be combined, it could be expanded to another talk. You must account for all of the possible noises and losses and atmospheric effects that affect your system. So it's a combination of theoretical models to analyze how important these are and what effects, what degradations they do, and then basically figure out strategies to make those effects go away if you can. So now we're open for questions, I guess.